And we will have one assignment to do with this. And the whole idea is that if you have a time series or a signal, there may be reasons why the fact that this is being generated by some underlying process would mean that there is correlations between the value of a sample, say stock price, and the samples or values that occurred before it. Okay. Can we exploit this observation in a systematic way? That's the question we can ask. And if we start asking these questions, what are the algorithms that come into play? What are the useful things that come into play? What are these things in the generic context? What are things that might apply specifically to finance? Becomes an interesting question. Okay? So the simplest thing we can do is we can say that, so we'll work always with discrete signals, not continuous signals. Okay? So if I write n here, that's days or months or depending on what scale you're working on. So you can imagine I can write that value of the signal or the stock price at time n as being given by something like, say, A1 S n minus 1 plus A2 S n minus 2 plus AP S n minus P plus some noise at time n. I'm free to write this if I thought that the current value of the signal that I see is a weighted combination or linearly weighted combination of P past values. Okay? So this I'm free to do. And what does this mean? This means this value, I'm saying, is a weighted combination of these past values. And if I took the one after that, that's going to be a weighted combination of this guy, this guy, this guy, and that guy. And that one would be a weighted combination of this one, this one, this one, this one, and this one. Okay. Yeah, so this is what I'm saying. So what we can ask is, given that someone has given you a lot of data, within this data that someone has given you, what's the best fitting values for A1, A2, up to AP? That's the question we can ask. Yeah. What would the best values be? It won't be perfect. You will never be able to predict S of n from these coefficients from past values perfectly, but what's the best fitting predictor given a window of data? So that's the question we can formulate. And immediately you will recognize that you're going to start from something like, let's say P equals 4. We're going to say S1, S2, S3, and S4 should predict S5. S2, S3, S4, S5 should predict S6, and so on. Correct? So that's the thing they can set up. So that would look immediately like a matrix of past values data. So that could be data of past values, of past values, multiplied by my coefficients, A1, A2, up to AP. This should achieve this one, which is a vector of current values. Correct? Is that kind of clear in your minds? Yeah? So what would the best values for these coefficients be in order to make this matrix times this as close as possible to this one? Yeah? And these ones are just adjacent values of the time series plugged in here. And these rows are constructed this way. Yeah? So take a small window, predict the next one, move a little bit, predict the next one, move a little bit, predict the next one. And as soon as you see this picture, you know enough to call this a regression problem. Yeah? Because in this p-dimensional space, this is p, this is number of data I have. In this p-dimensional space, I'm saying a linear function of these vectors should produce some target that I have here. Yeah, it's the regression problem. But this regression problem is popping out of a time series trying to regress on itself. Yeah, because this time series is trying to form as a regression on itself. Therefore, this process that I have written is known as an autoregressive process. Auto or known as AR. So that's a very, very common linear time series process. A process applied extensively in various places. The idea is very simple. Predict something as a linear function of the past and some noise that disturbs it. With me? So as soon as you are able to write that the way to solve for these regression coefficients, A1, A2, A3, is to do that, is to minimize the error between what this product gives you and this one gives you. This one is, if we call this, let's call this matrix Y, let's call this, I don't know what, theta shall we say, and let's call this some F. It's a vector. This is a vector of the number of parameters containing all the unknown parameters, and this is a matrix formed by all the inputs stacked together. Okay? So we can say what I then want to do is to minimize the error. So find theta by minimizing error. So I'm just writing error, but formally it's the least squares error. Okay? And I can write this error in two ways. You know this from the past. I can write this as a sum over all the data, the actual value of the time series, take away the sum of a, k, s, n minus k, k going from 1 to p. I can square it, add it up all over all the data, I have an error. Does that make sense? At every point in time, I have a linear function of the past samples which predicts what this is going to be. The difference is an error. I square it, add it up over all the data, I have an error. Okay? There are two things all of you should be able to do by now. You're sufficiently grown up. Is that write this as error, and you know enough to know if the job is to find these guys, differentiate this error with respect to each of these guys, equate it to 0, solve, and you tops out the answer to what the coefficient should be. Yeah, that much, that all of you should know now. The other thing all of you should know is to look at that one and say, so there's one way of writing it. The other way of writing it is that what I want is the matrix Y times theta minus F, the norm of that, because we have been writing L1 norm, I'm explicitly writing L2 norm of this. In matrix form, we should be able to write the same thing and minimize this with respect to theta. There's just two ways of writing exactly the same thing. And I have a reason for doing this. It will come out in a minute, okay? Is that clear, what I have tried to write? There's a error that needs to be minimized between what I have and what my model gives me. Squared, summed over all the data. The same thing can be written in matrix form. Multiply this matrix by the unknowns, you get a vector of all the predictions. Subtract this, take the norm, which is exactly the same as this one. Okay? What you will also recall from what we have done in the past is that if you want to minimize this with respect to theta, your best estimate of theta is obtained by y transpose y inverse y transpose f. And I think sometime in your previous life you called this a pseudo inverse. Correct? That much we kind of know. And I also add that you know how to minimize that. Okay, they're not two different things, they're just the same thing. It's a squared error, differentiate equal to 0, minimize is a standard way of doing it. Exactly the same thing can be written in matrix form, which makes life notations easier. Okay? Now comes some very interesting things we will learn starting from here. Okay. So this one is a least square solution. Oops. How might we use this? We might say somebody has given me a block of data. I might find what's the best fitting A coefficients over that data. Then I have learned something. And then along comes some new data. I can apply this model to predict. Yeah? So if I had some signal like that, some time series like that, this much, up to this point, you have given me some data starting from 1 to n. And I have looked at that and asked, what's the best fitting model that I can learn through this data? Yeah? And then after I have learned it, I want to ask the question, what happens here at n plus 1? Yeah? Then because I have learned these coefficients, I can say my sample value at n plus 1 is going to be a1 times this one, a2 times this one, a3 times this much, a4 times this much, and so on. Yeah, so I learned something, and then I can use it. Okay? The very interesting question that we can ask over here is that, can I do this recursively? That's one thing we will learn very quickly. And I would hold that if that's the only thing you learn from this course, then it's still worth paying your £9,000 fees or whatever. But immensely powerful thing that comes out of this. So that's one thing we'll look at. The second thing we'll look at is to write this as what is known as a state space model. And we'll come to what that is. And we will see how this state space model is learned through what's known as a common filter. Okay? That again is an immensely powerful method. Comes in, reinvented many times in the control signal processing and statistics literature. It enables us to do exactly the same thing with noise processes inserted. Okay, so that's the second thing we'll try and learn. And the third thing we will learn is, again, starting from the same formulation here. So here, if you look at the top row, I have said that my current sample is a linear function of the past plus some error. Okay? So this error is normally seen to be Gaussian with zero mean and some noise, constant noise. So normally when we fit models, we say, oh, we try to predict what happens, what comes out of the model. We ask the question, what's the difference between your target and the model prediction, minimize the error and so on. Some of you will know that there is a probabilistic side to this, which talks about likelihoods. Yeah, if you have done the advanced machine learning course, have you heard about maximum likelihood somewhere? Yeah, there is a probabilistic mirror of this, yeah, which says define the probability density of this, maximize the likelihood of data with respect to that. Okay, I'm not using that language here, just because I don't have very limited time. It turns out that if you held this constant, we have this machinery that we have, but it turns out you may not have this as constant in data that's not stationary. Data whose underlying properties can change with time. In financial jargon, this corresponds to volatility, and that can change with time. Okay? So there are models that try to bring that out, and they are known as stochastic volatility models. And we'll see a little bit about how one might write a stochastic volatility model, and what are tricks involved in estimating parameters of such a model. So that's the overall picture of what we will learn in about 3 hours of a massive field. Okay? There are stacks full of library books on this, on these topics, but we'll try and glean out of this the very basic essential ideas. What is it that you can do? What are the tools out there to model data in these ways? And if you happen to be in an environment where you can make money by doing it, then you know where to look. Okay, that's the level at which I'll leave you. Okay, so underlying all of this, so now comes homework. Let's go here. This off. I'll keep that. So we have touched on an autoregressive process and how we are going to estimate parameters of it. If you look at that pseudo-inverse that I have written, I have written theta hat equals y transpose y inverse, y transpose f. So you give me a block of data. I know how to learn the parameters a1 to ap, which are hiding inside my theta from that. Okay? Suppose I'm in a situation where data comes to me one at a time, and someone wants me to give me an online algorithm. Someone says to me, you are not allowed to train on all the data. If you have trained on all this data and estimated one value for the parameters, next data comes along, you need to update it. You're not allowed to rerun this. Yeah, so that's an online problem. What we will do in an online problem is we have calculated theta from n minus 1 samples. A sample is a point in data. And then I want to update this. So let's call this theta hat from n minus 1. Theta n minus 1 to theta hat n. So I want to update this without retraining. Let's say re-estimation. I'm not allowed to go back and do this one because that involves a matrix inverse, and matrix inverses are bad. There's a whole family of algorithms that are online algorithms that do precisely this. You have an estimate, a guess, or whatever, or correct solution of theta using n minus 1 data points. Along comes a new data, you want to update it. Along comes another data, you want to update it. Okay? And this is driven and without re-estimation because we don't want to do matrix inverse many times. So you know matrix inverse is of what complexity? If you want to invert a matrix, what's the complexity of a matrix inverse? Come across that? Cubic. So if you spend, I don't know, so many CPU hours inverting a 10 by 10 matrix, if the matrix becomes 20 by 20, you go cubic. You spend cubic in terms of complexity. So that's very complex thing. So that's, we don't want to do this. But it turns out somebody in the class is going to tell us how to do this without doing a matrix inverse. Because just before coming here, I ran into a guy by the name Liz, who teaches the Signals and Systems class. And there are hands up who are from the people from the signals and systems class. Oh yeah, so that I can see you. There's one, there's two. Anybody else? No, only two of you? I think there are 6 of you in the class. Yeah? So you have, so he tells me you know how to do this. Yeah? Yes, no? Yeah? Want to have a go? How about you?
I know it's weeks of common.
Give me some idea.
Oh, oh, you have to make state space. A state space.
Let's not go to state space yet.
No state space.
Yeah, let's still here. Give you a clue. I have matrix A. Okay. I write the inverse of the matrix as A inverse. Yeah. Suppose I have a matrix A plus some vector x times vector x transpose, and I want to invert this. Yeah, it's a sensible thing to do. So I have a matrix. I'm forming a new matrix. My new matrix is obtained by adding to this guy vector times vector transpose. Yeah, so you can believe this is true, right? So if this A is P by P, this X is P by 1, X transpose is 1 by P, so that will become a matrix P by P. You can add it, you can invert it. This is possible, right? There's a very elegant way of doing this. I can write this as the inverse of A. I'll just write this and then ask you to prove it, but that's quite nice. Take away A inverse X, X transpose A inverse over 1 plus X transpose A inverse X. You see why this thing is cool in a minute. So what is this? There's a matrix. Yeah. There's going to be a new matrix that's obtained purely by a rank 1 update, this is called. You are adding to this matrix a vector times its transpose. Why this is called rank 1 update, forget it for the moment, we'll think about it later. Okay? Someone wants for themselves the inverse of this addition, and they already know the inverse of A. Yeah, so that's the point. The inverse of A is already known. You want the inverse of A plus something. Okay? It turns out it's given by this formula. And in this formula, on the right hand side, there is no matrix inverse. The inverse of the matrix is already known. Okay? Is that kind of clear? So A inverse is already known. And someone says to you, what is A plus X, X transpose inverse? So that's the challenge. You do not know A, you know A inverse. Yeah? You want to find the inverse of A plus X, X transpose. It turns out I can find the inverse of this without further inverting a matrix. And these two people will tell me this is known as the matrix inversion lemma. Agree? No? Being true, didn't say this? He makes you sleep before saying this? I was going to bring him along, but okay, so this is immensely powerful, and it's actually usable in the problem that we know we want. Down here. Yeah. Look at this problem over here. Every time a data arrives, if I want to update my model, theta, I got to invert this guy, multiply by this matrix, multiply by that, and I get the answer. Okay? So now let's draw a picture. My matrix matrix Y is like that. That's my Y. It's going to be, let's say, n data by dimension p. Yeah. I'm going to multiply this by its transpose, which is going to be p by n. And then I'm going to take this whole thing and invert it. Okay? This inverse I can do as data arrives one at a time. Because this product I can write as the product of, let's draw a line here. If the matrix inside here I call y n minus 1, yeah, then I can write this product as y n minus 1, y n minus 1 transpose, plus, if I call this vector, what shall I call it? Small yn. Yeah, it's written this way, so to be consistent with my notation, I'll call this transpose, plus yn the transpose. So this whole thing, using n data, can be written as a sum of what it is with n minus 1 data plus a vector times its transpose. So inverting that whole thing is the same as inverting that. Yeah, I'll come back to this with some slides later, so you don't have to rush writing it down. Don't take pictures, I feel a bit nervous. I haven't done that properly. Yeah, so underlying the fact that I can estimate this linear model by this pseudo inverse, yeah, enables me, by borrowing this relationship, to do this sequentially. So if I had calculated theta n minus 1 from n minus 1 data given to me, then I can calculate from that theta n without further inverting a matrix. Okay, that's very fundamental and immensely powerful. And the resulting algorithm is called, one of you. Go on. Recursive. I'm waiting. Least squares. RLS. Yeah? It forms the basis of quite a lot of powerful things. Beam forming. So how do you have a number of antennas to respond with a small phase shift each, thereby forming a beam which is highly directional. So this is possible. So you can focus your antenna by having multiple antennas who operate with a phase lag between them. And if you did that, you have a very powerful directed beam. And if that beam is looking at something which is moving, you can adaptively track where the thing is going. Yeah? And this sort of thing is what drives that. So we'll come back to that. So the point that I want to make here is that I have a linear model. I can estimate parameters of that linear model. I can also do that sequentially. That's all there is. Okay? So, and that picture should be in your mind. I have a linear model, which is my autoregressive process. I can estimate parameters. Let's say explicitly write pseudo inverse. And I can do it recursively. Okay. So let's take a pause to digest that. And I'm going to pass to you your coursework number 2 The way we'll do this is ordered, okay? This is ordered in alphabetical order by your surname. I insist on saying this because what's your name? Peter is not by name Peter. No, not that I'm referring to Peter here. Right? So it's ordered by surname. So you're the only Peter here. Peter was taken as an example. Not that you did anything wrong. Okay, so this is ordered by surname. So just as it passes along, just look at it, pick your one, and then pass it on. Yeah, quickly. Don't take your friend's one. Let's grab the friend. So go zigzag this way. And once that goes, let's send this from back. So this is coursework 1, uncollected ones. This probably will go faster because yeah. Yeah, correct. Yeah, that's the starting point. That's the motivation. When you, so you can't do if you are doing adaptive beamforming, matrix inverse on a chip is very difficult.